In this video, I'll be going over vectors. So here's a definition. A vector is a quantity that contains a magnitude and a direction. So some common vectors are velocity, acceleration, force, or wind speed. So let's talk about wind speed for a sec and why this is a vector. So when a weather person is saying what the wind is forecasted at, they might say something like 15 miles per hour from the west. So what we would say is this 15 miles per hour is the magnitude. It's, the strength of the quantity. And then by saying from the west, that gives a direction. So vectors always have these two parts. This is contrasted with what is called a scalar, which can be described simply as a magnitude. I guess I spelled units wrong here. So something that is just a magnitude, like length, area, or volume. So length, you might say that the length of the chalkboard is 10 feet. You wouldn't say 10 feet to the west or something like that. So we can represent a vector geometrically as a line segment with an arrow. So we talk about vectors with an initial point and a terminal point, so just the ending point. So we can draw a vector in any direction. So this vector that I just drew is shorter than this vector. So this first vector has a greater magnitude than the second vector. If I drew a vector in the opposite direction, that will be reflected in how we algebraically represent the vector. So we'll be seeing that here in a second. So we can add vectors in a couple different ways. We can do this geometrically. So suppose I had this vector, let's call it V, and when we write a vector, we can put a little arrow above it. And then let's say I had this vector W. Okay, so if I wanted to add V plus W, what we'd say is, well, I would draw a vector V, like this, and then I take vector W, and I put the head, or the tail of vector W, and attach that to the head of vector V. And so this vector right here is V plus W. And we call this the resultant vector. It's just the result of adding these vectors together. So this first way that we've written this is geometrically. So we can add vectors geometrically. We can also do this algebraically. So let's say we have vector V is equal to 2, 3, and then vector W is equal to -4, 1. Okay, so if we want to find V plus W, all we do is we add the like components. So we're going to add the 2 and the -4 together first. So 2 plus -4, and then 3 plus 1. So we end up with -2, 4. All right. And so what does this mean geometrically? Well, if we think about this on the xy plane, which is what we will do. So vector V, we say is 2 in the horizontal direction, 3 in the vertical direction. So this vector right here, we say is vector V. And then vector W is -4 and +1. So vector W will be here. Okay. So if we were to add these vectors together, I would take vector W and place the tail of vector W at the head of vector V, and then the resultant vector is this guy right here. That's going to be V plus W. And just notice how that corresponds to what we found when we added this algebraically. I have -2 in the horizontal direction, so I'm at -2 along the horizontal axis, and then I'm at +4 along the y-axis or the vertical axis. Okay, so we can add these algebraically or geometrically. Often, though, we're going to do this algebraically because it's easier to be precise. And then the other basic operation we can do with a vector is called scalar multiplication. So suppose I have this vector, let's call it vector v. All right, so suppose I wanted to multiply v by, not 5, let's say 3. What that's going to do is going to take our original vector v, and it's just going to increase the magnitude times 3. So I'm going to have the same direction, but now it's going to be 3 times as long. And again, it's hard to be precise when we're doing this geometrically, but that's the idea. Okay, so what we notice is that we call this a scalar because it's just a magnitude, right? 3 is just a scalar. So if the scalar is above 0, then the resultant is in the same direction. Okay, so that's what we saw there. We multiplied by 3. This is just increasing the magnitude 3 times, and we're in the same direction. Similarly, let's say I have negative 2v. Well, now the vector is going to be going in the opposite direction, and it's going to increase the magnitude by 2. So if the scalar is less than 0, the resultant is opposite direction. Okay, and then if we were ever to multiply a vector by 0, that's going to give us a vector that has magnitude of 0. One thing that we want to be able to do is take a vector and break it down into its horizontal and vertical components. So for example, if we know the magnitude and the direction angle of a vector, we want to be able to write it in the form kind of how I had written one in the previous slide. Okay, so how do we do this? Well, if we think of a vector in the coordinate plane like this, there's some angle here, and I'm going to call the magnitude r. That's just the length of that vector. So if I wanted to know the vertical component, let's call it y, vector w sub y, and let's just call this vector w, and then this component down here is vector w sub x, which is just the horizontal component. So if I wanted to find w sub y, well, let's just use a trig function. So sine of theta is equal to w sub y divided by r, and we're going to give this component a positive value by using the absolute value sign, and then cosine of theta is equal to magnitude of x divided by r. So we could say r sine theta is equal to the vertical component, and then r cosine theta is equal to the horizontal component. Alright, so here's an example. Find the magnitude of the horizontal and vertical components for vector v with a magnitude of 8.3 and a direction angle of 121.3. So if the angle is 121.3 degrees, that means we're going to be in quadrant 2, and magnitude is 8.3. So this angle here is 121.3 degrees. So what we want to do is we want to find this vertical component and then this horizontal component. So all we need to do is we can set up trig equations. So cosine of 121.3 degrees is equal to the adjacent side, which I can call v sub x divided by 8.3. So 8.3 cosine of 121.3 degrees. And then I'm going to go do the same process for the vertical component, but this will just simplify down to 8.3 sine of 121.3 degrees. So type both of these into the calculator, and for the horizontal I'm going to get about 4.31, and for the vertical I'm going to get 7.092, let's call it. Now we want to make sure both of these are positive, even though the horizontal component is in the negative, like the negative x direction, but it's positive because it's a magnitude, right? And if we're talking about magnitude, we always want to use a positive value. So, for example, I'm 6 feet 5 inches tall. I wouldn't say, no matter kind of, if I'm standing on my head, I wouldn't say I'm negative 6 feet 5 inches tall, or if a length is in a different direction. If we're talking about what that length is, we always use a positive value. Okay, so we found the components here. So there's two ways we can write it. We can write it like this: 4.31, comma 7.092, or we could write it 4.31i plus 7.092j. Now I want to clarify something. There's a little bit of a nuance here that I made a mistake on. So the question here is asking us to find the magnitude of the vertical and horizontal components. So these values satisfy that answer. Those 4.31 is the horizontal magnitude, 7.092 is the vertical magnitude for this vector. However, what I wrote down here we call component form. And when we write a vector in component form, we want to, we don't just put the magnitudes. We want to be able to identify which direction this vector is going in. So the horizontal component is going to be negative in each of these instances. So negative 4.31 comma 7.092 would be that vector in component form, or negative 4.31i plus 7.092j would be the other way we can write it in component form. So we use I here to represent the horizontal component, and we use j to represent the vertical component. So we'll see vectors written in either of these ways. So sometimes we'll want to go in the opposite direction. So if we're given a vector v, which has components negative 2, negative 5, we want to know the magnitude and the direction. So really doing something like this, it's just like finding some values in a triangle. So negative 2, negative 5, this vector looks like this. So what we can do is we just need to find the hypotenuse of this right triangle, and we need to find the central angle. Okay, so let me kind of relabel this. So negative 5 here and negative 2 here. Okay, so to find the magnitude r, we're just going to say r squared is equal to negative 5 squared plus negative 2 squared. R squared is 29, so r is equal to the square root of 29, and we only use the positive value here because we want our magnitude to be positive. And then to find that central angle theta, we're going to say tangent of theta is equal to negative 5 over negative 2. So tangent of theta is equal to 5 halves. And then what we do from there is we do tangent inverse of 5 halves is equal to theta, and we use the calculator to evaluate that. And in the calculator, we get 68.199 degrees. Now the problem is that would be this angle in the first quadrant, 68.199 degrees. So what we need to do is we need to add 180 to get that angle into quadrant 3. So plus 180 degrees, and we end up with 248.199 degrees for the direction angle. All right, so we've solve for both of these parts. The magnitude is square root of 29, and the direction angle is 248.199 degrees. All right, let's do one more example. Find the component form for a vector of magnitude 40 miles per hour and a direction angle of 330 degrees. Now, I always like sketching out what we're looking at. So the magnitude is 40, and this angle here is 330 degrees. So if we think about this as a right triangle, we want to find this x value and this y value. So because this is in quadrant 4, the y value, or the vertical component, should be negative, and the horizontal component should be positive. So we're going to say 40 times cosine of 330 degrees will give us the x value, and then 40 sine of 330 degrees will give us the y value. So punching this in, for x we're going to get about 34.641, and for y we're going to get negative 20. Okay, so that makes sense with our diagram. Whoops. Negative 20 here for y, 34.641 for the x. So in component form, I'll write it like this, 34.641, comma, negative 20. Or we can write this 34.641, getting ahead of myself, 641 I minus 20j. So that's it. In the next video, we'll be going over some operations with vectors and the dot product.